Good morning, students. Today we are going to see about Chapter 2, the remaining problems, question number 30. Okay. A spherical capacitor has an inner sphere of radius 12 centimeter and an outer sphere of radius 13 centimeter. The outer sphere is Earth and the inner sphere is given a charge of 2.5 microcoulombs. That is, there is inner sphere and this radius is 12 centimeter and outer sphere of radius 13 centimeter. This is of 13 centimeter and the outer sphere is earth and the inner sphere is given a charge of 2.5 coulomb. Inner sphere is given the charge of 2.5 microcoulomb and the space between the concentric circles, this space is filled with a liquid of dielectric constant 32. Dielectric constant value will be 32. So here determine the capacitance of the capacitor. That is the first question. And the second question is, what is the potential difference of the inner sphere? What is the potential difference of the inner sphere? Third question is, compare the capacitance of this capacitor with that of an isolated sphere of radius 12 centimeter. Explain why the latter is much smaller. Why the latter is much smaller. Okay, so we can go for the solution. So what are the things given that R2 is equal to 12 centimeter, that can be written as 0.12 in meters, and then R1 is equal to 13 centimeter, that will be 0.13 meters. Then the charge Q is equal to Q in the inner sphere will be equal to 2.5 microcoulomb is equal to, if we want to convert it into coulomb, means microcoulomb to coulomb means into 10 to the power of minus 6, 2.5 into 10 to the power of minus 6 coulomb. So epsilon r be the dielectric constant, that will be equal to 32. Dielectric constant of a liquid will be epsilon r is equal to 32. So then what is the first question asked? Determine the capacitance of the capacitor. So the formula for this will be C is equal to 4 pi epsilon naught epsilon r into R1 R2 divided by R1 minus R2. This will be the formula to find the capacitance of the capacitor. Epsilon naught be the permittivity of free space and the value will be 8.85 into 10 to the power of minus 12 coulomb squared Newton inverse meter inverse squared. So here in this formula we can have the value of 1 divided by 4 pi epsilon naught. 1 divided by 4 pi epsilon naught value will be 9 into 10 to the power of 9 Newton meter squared coulomb inverse squared. So if we substitute the values of in this formula, that is 4 pi epsilon naught epsilon r r1 r2 divided by r1 minus r2, we will get the answer, and simplify means we will get the answer as 5.5 into 10 to the power of minus 9 farad. Hence the capacitance of the capacitor we have find it out. We can go for the second question. What is the second question? Actually, what is the potential of the inner sphere? What is the potential of the inner sphere? To find the potential of the inner sphere, we can have the formula V is equal to Q divided by C. V is equal to Q divided by C. Q value already we know it as 2.5 into 10 to the power of minus 6. Q value it is given as 2.5 into 10 to the power of minus 6 coulombs, and C value will be 5.5 into 10 to the power of minus 9. Substitute the values and you will get the answer as V is equal to 4.5 into 10 to the power of 2 volts. And we can go for the third question, C part question. Compare the capacitance of this capacitor with that of an isolated sphere. Instead of a capacitor, we are having an isolated sphere of radius 12 centimeter. Explain why the latter is much smaller. Why it will be smaller. We can go for the third part. Radius r is equal to 12 into 10 to the power of minus 2 meter, and then the capacitance can be C dash is equal to 4 pi epsilon naught into r. Substitute the values, 4 into pi into epsilon naught value 8.85 into 10 to the power of minus 12 and R value will be 12 into 10 to the power of minus 12 will give you the final answer as 1.33 into 10 to the power of minus 11 farad. 10 to the power of minus 11 farad. Here we need to explain why it is smaller. The capacitance of the isolated sphere is less in comparison to the concentric spheres. This is because the outer sphere of the concentric spheres is Earth. The outer sphere is Earth. Already we have learned it in the sum. Hence, the potential difference is less and the capacitance is more than the isolated sphere. Capacitance is more than the isolated sphere. So we can go for the question number 31. Two large conducting spheres carrying charges Q1 and Q2 are brought close to each other. Is the magnitude of electric force between them exactly given by Q1 Q2 divided by 4 pi epsilon naught R squared, where R is the distance between their centers. So what we can see is two large conducting spheres. Two spheres are there having the charges Q1 and Q2, and the distance between these two their centers can be taken as r small r. Okay, so magnitude of the electrostatic force between them will be having this formula q1 q2 divided by 4 pi epsilon naught r squared. Okay, we need to find out. And the second question will be, if Coulomb law involved 1 by r cube dependence instead of 1 by r squared, would Gauss law will be true? Still true. Gauss law true. Whether we have to find out whether Gauss law will be true. Okay. And then third question will be, a small discharge is released at rest point in an electrostatic field configuration. Will it travel along the field line passing through that point? And then fourth question is, what is the work done by the field of a nucleus in a complete circular orbit of the electron? What if the orbit is elliptical? So similarly, 7 questions are given. First, we can see the first question. The force between the two conducting spheres is not exactly the expression. The expression given is Q1 Q2 divided by 4 pi epsilon naught r squared. This will not be the exact expression we have, because there is a non-uniform charge distribution on the spheres. In the sphere, we are having non-uniform distribution, so that this equation will not be applicable. Hence, Coulomb's law is not applicable. Hence, this Coulomb's law is not applicable. That is the first answer. And then, if we go for the second one, it is asked that whether the Gauss law is still be true. Gauss law will be still be true. If we go for that, means here the Gauss law will not be true if the Coulomb's law involved will be 1 by r cube dependence instead of 1 by r squared r on r squared on r. So this Gauss law will not be true. If we go for the third question, a small discharge is released at a rest point in an electrostatic field configuration. Will it travel along the field line passing through that point? Will it travel along? We are keeping a discharge at a rest point in an electrostatic field configuration. Then what will happen? Whether it will travel or not. So if we go for the third one, yes, if a small discharge is released at a point in an electrostatic field configuration, then it will travel along the field lines. It will travel along the field lines, magnetic field lines, passing through the point only if the field lines are straight. If the field lines are straight, means this discharge will be having the electrostatic field configuration. It will travel along the field lines, passing through the point only if the field lines are straight. This is because the field lines give the direction of acceleration. The field lines are going to give the direction of acceleration, in which direction the acceleration is acting, and not of velocity, and not of velocity. It is not giving about the explaining about the velocity. Okay, this is about the third question. Then what is the fourth question asked? What is the work done by the field of a nucleus in a complete circular orbit of the electron? What if the orbit is elliptical? Orbit will be, if the orbit is elliptical, means what will happen? And what is the work done by the field? Both the things we need to find out. Okay. So Whenever the electrons move in a circular orbit, the work done by the force of the nucleus is zero. If the electron is moving in a circular orbit, means the work done will be zero. Work done will be zero. Either circular or elliptical, the work done by the field of nucleus is zero. The work done will be of zero. So then we go for fifth question. We know that electric field is discontinuous across the surface of a charged conductor. So in the surface of a charged conductor, the electric field will be discontinuous. It will not be continuous. Is electric potential also discontinuous there? Electric field is discontinuous. We have to find out whether the electric potential will also be discontinuous. No. No electric field is discontinuous across the surface of a charged conductor. However, electric potential is of continuously having that. Okay. So if we go for the next question, F question. What meaning would you give to the capacitance of a single conductor? Capacitance of a single conductor. The capacitance of a single conductor is considered as a parallel plate capacitor with one of its two plates at infinity. In a parallel plate capacitor, if we want to have it as a single conductor, means one plate is at infinity. One plate is to be kept at infinity. And what is the final question? Guess the possible reason why water has a much greater dielectric constant. Much greater dielectric constant. The dielectric constant of water will be of 80, and of mica will be of 6. Mica will be of 6. We have to find the reason why the water has much greater dielectric constant. Water has much greater dielectric constant. Okay, because water has an unsymmetrical space as compared to mica. If we are comparing with that of mica, the space will be unsymmetrical. The space will be unsymmetrical, and it has a permanent dipole moment. It is having a permanent dipole moment. It has a greater dielectric constant than mica. So the dielectric constant will be greater than mica. Greater than mica. This is about the 31st sum. Then we can go for 32nd sum. So a cylindrical capacitor has two coaxial cylinders of length 15 centimeter. So the length of the cylinder will be of 15 centimeter, and the radii will be 1.5 centimeter and 1.4 centimeter. The outer cylinder is earthed. What we are doing is, the outer cylinder is similar to that of first sum. The outer cylinder will be earthed, and is earth, and the inner cylinder is given a charge of 3.5 microcoulombs. So determine the capacitance of the system and the potential of the inner cylinder. Neglect effects, that is bending of field lines at the ends. Bending of the field lines at the ends to be negligible. So L is equal to 15 centimeter. If we convert it into meter, means 0.15 meter, and the radius R1 is equal to 1.5 centimeter. If it is on meter, means 0.015 meter, and the radius of the inner cylinder R2 is equal to 1.4 centimeter, is equal to 0.014 meter. 0.014 meter, and then radius R2 is equal to R2 we have done, and then Q is equal to, charge Q will be is equal to 3.5 microcoulombs, is equal to 3.5 into 10 to the power of minus 6 coulombs. To convert microcoulombs into coulombs, we have to multiply it with 10 to the power of minus 6 value. So the formula will be C is equal to 2 pi epsilon naught L divided by log of E of R1 by R2. R1 by R2. So epsilon naught be the permittivity of the free space. Epsilon naught will be the permittivity of the free space. 8.85 into 10 to the power of minus 12 Newton inverse meter inverse square Coulomb squared. Coulomb squared. So C is equal to 2 pi into 8.85 into 10 to the power of minus 12 into 0.15 divided by 2.3026 log of 0.15 divided by 0.14 to the base 10. So if you find the values and substitute and simplify, means you will get the answer as 1.2 into 10 to the power of minus 10 farads. So potential difference of the inner cylinder V is equal to Q divided by C. The Q value will be 3.5 into 10 to the power of minus 6. The Q value will be 3.5 into 10 to the power of minus 6 divided by 1.2 into 10 to the power of minus 10. Will gives you the answer as V is equal to 2.92 into 10 to the power of 4 volts. 2.992 into 10 to the power of 4 volts. A question number 33. A parallel plate capacitor is to be designed with a voltage rating of 1 kilovolts using a material of dielectric constant 3 and dielectric strength about 10 to the power of 7 volt meter inverse. So, dielectric strength is the maximum electric field a material can tolerate without breakdown, that is, without starting to conduct electricity through partial ionization. For safety, we should like the field never to exceed, say, 10% of the electric strength. What minimum area of the plate is required to have a capacitance of 50 picofarads? So, potential rating of parallel plate capacitor V is equal to 1 kilovolts. This can be converted into volt, that will be 1000 volts. So, dielectric constant epsilon R is equal to 3. Dielectric strength will be of 10 to the power 7 volt per meter, that is voltmeter inverse. Voltmeter inverse. The field intensity never exceeds 10% of the dielectric strength. So that E will be is equal to 10% of 10 to the power of 7. Well, gives you 10 to the power of 6 voltmeter inverse. Voltmeter inverse. So capacitance of a parallel plate capacitor will be C is equal to 50 picofarads. It can be converted into farads, will be equal to 50 into 10 to the power of minus 12 farads. So using the formula, D is equal to V divided by E. D is equal to V divided by E. The V value will be 1000 and then E value will be 10 to the power of 6, will gives you 10 to the power of minus 3 meter. So the capacitance formula will be C is equal to epsilon naught epsilon R A divided by D. Epsilon naught epsilon R A divided by D. So where A will be the area of the glass plate. A will be the area of the glass plate. And epsilon naught already we know that is the permittivity of free space, and the value will be 8.85 into 10 to the power of minus 12 Newton inverse coulomb squared into meter inverse squared. Meter inverse squared. Okay. So that A will be equal to C into D divided by epsilon naught epsilon r, epsilon naught epsilon r. Bring the C to this side. Okay, 50 into 10 to the power of minus 12 into 10 to the power of minus 3 divided by 8.85 into 10 to the power of minus 12 into 3. Now, if we simplify all these things, we will approximately get as 19 centimeters squared. Hence, the area of each plate, will be 19 centimeter inverse. Question number 34. Describes schematically the equipotential surface corresponding to a constant electric field in z direction, a field that uniformly increases in magnitude but remains in a constant, that is z direction, that is on z direction. And then C, third question will be a single positive charge at the origin, and fourth question is a uniform grid consisting of long equally spaced parallel charged wires in a plane. So these are the four questions asked here. So it is acting on the equipotential surface. So the A question will be equidistant planes parallel to the xy plane or the equipotential surfaces. So if it is a equipotential surface means, and the planes equidistant planes will be parallel to xy plane. And second question asked is, what is the second question asked? A field that uniformly increases in magnitude but remains in constant, say, z direction. So planes parallel to XY plane are the equipotential surfaces, with the exception that when the planes get closer, the field increases. If the planes come closer to each other, means it will the field will also increases. And if we go for the C question, a single positive charge at the origin, a single positive charge is kept at the origin, so that concentric spheres centered at the origin are equipotential surfaces. Concentric spheres centered at the origin are equipotential surfaces. And then if we go for the D question, a uniform grid consisting of long equally spaced parallel charged wires. Long equally spaced parallel charged wires in a plane. So if you go for that plane, a periodically varying shape near the given grid is the equipotential surface. This shape gradually reaches the shape of planes parallel to the grid at a larger distance. If it is for a larger distance, means it will become as the shape of the planes will becomes parallel. The shape of the planes will become parallel. That is about the 34th question. Then we can go for the 35th question. In a Van de Graaff type generator, a spherical metal shell is to be 15 into 10 to the power of 6 volts electrode, and the dielectric strength of the gas surrounding the electrode is 5 into 10 to the power of 7 volt meter inverse. What is the minimum radius? What is the minimum radius of the spherical shell required? Okay, so if we go for the thing, B is equal to 15 into 10 to the power of 6 volts, and the dielectric strength of the surrounding gas will be 5 into 10 to the power of 7 volt per meter inverse, and then E will be is equal to 5 into 10 to the power of 7 volt per meter. That will be dielectric strength. This will also equal to the dielectric strength. So minimum radius of the spherical shell required for the purpose is given as R is equal to minimum radius R is equal to V divided by E. V value will be 15 into 10 to the power of 6, and E value will be 5 into 10 to the power of 7. 5 into 10 to the power of 7. If you simplify, you will get the answer as 0.3 meter. If we convert it into centimeter, means 30 centimeter. So the minimum radius of the spherical shell required is 30 centimeter. Minimum radius of the spherical shell required is 30 centimeter. Then we go for 36th sum. A small sphere of radius R1 and charge Q1. The radius of the sphere will be R1 and the charge of the sphere will be Q1, is enclosed by a spherical shell of radius R2 and charge Q2. The radius of the another spherical shell is R2 and the charge will be Q2. Show that if Q1 is positive, charge will necessarily flow from the sphere to the shell. When the two are connected by a wire, no matter what the charge Q2 on the shell is, we can go for the solution. According to Gauss law, the electric field between a sphere and a shell, first one is the sphere and the second one is the shell, is determined by the charge Q1 on a small sphere. Hence, the potential difference V between the sphere and the shell is independent of charge Q2. It is independent of the charge Q2. For positive charge Q1, the potential difference V is also positive. So this is about the 36th question. So what they are giving, according to Gauss law, the electric field between the sphere and a shell. We are taking a sphere and a shell. So, determined by the charge Q1 on a small sphere will be the potential difference V and the between the sphere and the shell is independent of the charge Q2. For positive Q1, the potential difference V is also positive. For positive Q1, V will also be, potential difference will also be positive. Then we can go for the 37th question. Answer the following. The top of the atmosphere is at about 400 kilovolt with respect to the surface of the earth, corresponding to an electric field that decreases with altitude. Near the surface of the earth, the field is about 100 volt meter inverse. Why then do we not get an electric shock as we step out of our house into the open? Assume the house to be a steel gauge, so there is no field inside. If the house will be of a steel cage means there will be no field inside will not having field. Okay, so that B question is, a man fixes outside his house one evening a 2 meter high insulating slab, 2 meter high insulating slab carrying on its top a aluminium sheet of area 1 meter squared. On the insulating slab, in the top we are having an aluminum sheet of area 1 meter square, aluminum sheet of area 1 meter square, so that 2 meter high insulating slab, on the top we are having a aluminum sheet of 1 meter square, aluminum sheet of 1 meter squared, so that will he get an electrical shock if he touches the metal sheet in the morning? If he touches the metal sheet in the morning, this is the second question asked. And the discharging current in the atmosphere due to the small conductivity of air is known to be 1800 amps on an average over the globe. Why then does the atmosphere not discharge itself completely in due course and become electrically neutral? So all the things to be charges to be discharged, and it should not go as a, it is not going as a electrically neutral. In other words, what keeps the atmosphere charged? Which thing keeps the atmosphere always as a charged thing? So there is the C question, and then we can go for D question. What are the forms of energy into which the electrical energy of the atmosphere is dissipated during a lightning? Dissipated during a lightning, and some hint is given there. So we can go for the solutions. So what is the first question and question and the solution can be. So first solution for first question will be, we do not get an electric shock as we step out of our house. If you are stepping out of our house, we doesn't get the electric shock. The reason is, original equipotential surfaces of open air changes, keeping our body and the ground at the same potential. If our body and the ground will be on same potential means, then we will not get the electric shock, we will not get the electric shock. Okay, this is about the first question. Then we can go for the second question. Yes, the man will get an electric shock if he touch the metal slab next morning. If the man is going to touch the electric slab next morning means, sorry, metal slab next morning means he will get the electric shock. The steady discharging current in the atmosphere charges up the aluminum sheet. In the atmosphere, some of the discharging current, steady discharging current is there in the atmosphere, so that the aluminum sheet gets charged. As a result, its voltage rises gradually. The rise in voltage depends on the capacitance of the capacitor formed by the aluminum slab and the ground. Aluminum slab and the ground. Then the third question will be, the occurrence of thunderstorm and lightning charges the atmosphere continuously. Hence, even with the presence of discharging current of 1800 ampere, the atmosphere is not discharged completely. The two opposing currents are in equilibrium and the atmosphere remains in neutral. Atmosphere will always be remaining in neutral. Then what will be the fourth one explanation means, during lightning and thunderstorm, light energy, heat energy, and sound energy are dissipated in the atmosphere. So, what are all the energies dissipated in the atmosphere means, what are all the energies? It is light energy, heat energy, and sound energy. All the things are created in the atmosphere while lightning and thunderstorm appears in the atmosphere. Lightning and thunderstorm appears in the atmosphere. This is about the question number 37. So we have completed the lesson 2, numericals. Thank you, students.